In order to get this here, what we kind of talked about is if I want to graph this, and this is what we're going to do down here in terms of figuring out what this is. We could use our calculator, but if this is a line, and then actually, if I was going to be a little more specific, since we have an interval of 0 to 1, this is actually a line segments because we have a distinct starting point and a distinct ending point. So the way that we can do this is what we're going to do in these next 4 problems anyway, so we'll kind of introduce this right now. Think about what would happen is at the time of 0. Well, at the time of 0, if I plug it into this equation, wouldn't I have at the time of 0 an x position of 0? And then if I took the time of 0 and I plug it into this equation, wouldn't I just get 2 minus a 0, which is 0, 2? So the initial point to this guy, at the time of 0, we would be at this point 0, 2. All we need to draw a line or a line segment is 2 points. So what we then just do is plug in the value at the time of 1 and identify what's the x coordinate and the y coordinate at that particular time. So take the time of 1, plug it into this equation, and this is just saying x equals t. So if t is a 1, so is x. Then take the time of 1 and plug it into your y equation. So if I do 3 times 1, that's 3. 2 minus 3 is a negative 1. So at the time of 1, we are now at the point 1, negative 1. This was our first point. This was our final point. So we went from here to here. I've been having you draw little arrows to indicate our direction. So that's our little line segment. And we would have gone from this point to this point. So that was the direction in which we were traveling. Okay. Yesterday, I had you use your calculator. What we're going to now do in 12, 13, 14, 15 is to do all of these, but without using our calculator. You're going to write a Cartesian equation. Oh, real quick, how do we get a line out of this? Because this is what that writing a Cartesian means. Think about y equals 2 minus 3t. Aren't we saying right here that t is equivalent to x? So I really could get rid of the t in this case, substitute an x, and then notice what we're looking at. Doesn't this have a y-intercept of 2? Which is we should have. And then our slope is a negative 3. So notice how I went down 1, 2, 3, right 1. So I just have that over the interval of time that we're given here, 0 to 1. So all of these, when we write what we're calling a Cartesian equation, that just means an xy equation, it's usually some sort of algebra, some sort of a substitution. Then I want you to graph the equation, and then I want you to show the direction in which we would have been traveling. Okay? So for number 12, if we kind of think about what this should be giving us, when we would have done these yesterday, we hopefully talked about enough of these to know that since x is cosine, y is sine, and that you're going to go from 0 to pi, that if we kind of recall what this would mean, this should be a semicircle because the coefficient of both of these are 1, and that semicircle would have a radius of 1. All right, normally it's a full circle, but the interval of 0 to pi, since the x is paired with cosine and y is paired with sine, is basically going to behave just like our unit circle and go counterclockwise in the first and the second quadrant. But as these get harder, here's how we really want to approach these. And it's basically like a little XY chart, but we're going to be doing it with a TXY chart. And it's similar to what we did in that number 11 a second ago. Take this initial time of 0 and then plug it in. And then find your x position and your y position at that time. So if this is my x position, cosine of 0 would have been a 1. And then the sine of 0 would have been a 0. So that's how we get the initial point. That's how we would know that this is our first point when we start talking about our direction. I'm going to pick one in between. So I'm going to pick pi over 2. And do the same thing. The cosine of pi over 2 is 0. The sine of pi over 2 is 1. So then this was our second point. That's how we would know that that's the direction that we went if we didn't already kind of know how this behaves, if we have some different functions. And then our last one, which is pi, this should be where we end. The cosine of pi is a negative 1. Sine of pi is 0. So that's why we stop here. This is our final point, our terminal point. And we would now know we went from here to here to here. That's how we know our direction. That's how we would also know that's a semicircle. The Cartesian equation, let me create some space in here. Let me do this in red since it's a little jumbled, is based off of the identity that cosine squared plus a sine squared is equal to 1. Well, think about what cosine is equivalent to here, right? Isn't cosine just x? So this would become x squared. And then sine squared, here's what sine is equivalent to. Sine is equivalent to a y, so y squared equals a 1. That's the equation of a circle whose center is the origin and whose radius is 1. All right, so that's what we call our Cartesian equation. The xy plane is the Cartesian plane. All right, that's our answer for that. All right. So now 13, we should be able to still, this is a pretty obvious one. Hopefully, after what we did yesterday, we should probably be able to graph this without having to do that, where we know x is paired with cosine, and then the y is paired with our sine. So it really should just take on the unit circle ideas. So here's 0, here's pi over 2, here is pi. We should only get half of this. Our x would go left and right 4. So let's say this is 4. Let's say this is -4. But our vertical should go up to 5, and then if we had it, we'd be down here to -5. But since our interval is only 0 to pi, instead of this full ellipse, it's just half of an ellipse, and it should go in the same direction as the unit circle. But again, if it's a little more complicated and we don't really know what's what, the way we can always do these is with our little chart here. Get rid of some of this. So let's pick 0, let's pick pi over 2, and let's pick pi again. And then that should produce this graph off to the right. So if I take my x, the cosine of 0 is 1, but then I'm going to multiply by 4. So that's a 4. Your y position at the time of 0, sine of 0, 0 times 5 is 0. So that tells us 4, 0 is this initial point. If we do pi over 2, cosine of pi over 2 is our 0 now. The sine of pi over 2 is the 1 that you're going to multiply by 5. So then that tells us that this is our second point. That's how we would know the direction in which we were traveling. Okay. And then pi is obviously going to take us here. So if you want to fill that out, that's fine. But that would be a -4, 0. And then we're all set. The Cartesian equation, same principle as number 12, where we're dealing with the idea that cosine squared plus sine squared equals a 1. So in this question right here, I'll solve for it up top. So cosine equals, divide the 4 over. What cosine equals in this case is an x over 4. If I solve this one for sine, I'm going to divide the 5 over. So that would become y over 5. So instead of a cosine squared, we write that as x over 4. Instead of sine squared, what sine is equivalent to is y over 5. That equals a 1. This is the equation of an ellipse that gets stretched horizontally 4, vertically 5, and there are no shifts with the x and the y, so we're centered at 0, 0. Okay. 14 is the first one where we don't really know what this looks like. So now very much, if you didn't have a calculator in your hand, we would want to set up our little TXY chart. So in this one, that's definitely how we want to get this started. So we'll do our t, and then what's our x position at that time? What is our y position at that time? We're going to start at 0. Pretty straightforward. Root 0 is 0, and then y equals t. Our t is a 0. So when we go to graph this, The initial point is a 0. So this is our first point. If I go to the time of 1, I'm going to get a negative root 1. So that's a negative 1 for x. If I plug it into y equals t, then y would just equal 1 as well. So my next point would be negative 1, 1. Since this is my second point, I know that I went in that direction, first to second. I would do another point because you don't know if this is a line. We don't know if it's curved. So I wouldn't connect those just yet. Let's do one more point. Pick a good number. And by good, I mean 4, so that we can take the square root of it nicely. This would give us a negative 2. And then since y equals t, if our t is 4, so is our y. So now go to negative 2, 4. We're way up here. What we have, and this is our third point. Let me create some space. What this should be is a half parabola. All right, and then it does continue on forever. We just have enough now to where we can sketch this. Since this was first, second, third, our direction is this direction. So it actually kind of goes in the opposite direction of how our parabolas would normally get graphed. So you would need to make sure our arrows or vectors eventually are showing that we're going off in that direction. Okay. For our Cartesian equation, again, it's usually some sort of a substitution. This one's actually the easiest. Think about what y equals. Doesn't y equal t? So if I took y equals a negative root t, isn't that really the same as y equals a negative root y? Because y and t are equivalent. I would take that. That's a totally fine answer. But if we want to look at our graph and compare them, square both sides, doesn't this really give us x squared on the left, y on the right? So aren't we looking at a parabola whose vertex would be 0, 0 that opens upwards? We're only getting a half of it, though, because of the domain of time that I gave you. Okay. All right, and then our last one, 15. This, just for future reference, we know this should be a line for the same reason you know an equation is a line under normal circumstances. Notice how the degree of x is a 1 and the degree of your y variable is a 1. That's what a linear equation needs in normal function notation. So even in parametric, it's the same thing. So this should be a line. But we don't necessarily know where it starts, where it ends, all that good stuff. So we're going to set up our little table. Negative infinity to infinity, you can't really plug any of those in, so that's not necessarily a big deal. We're going to still start at 0. X would be 1 minus 0, so 1. Y would be 1 plus 0, which is 1. So on our graph, plot the point 1, 1. Then I'm going to pick the x value or time value of 1. 1 minus 1 is 0. 1 plus 1 is a 2. So 0, 2 is the next point. If we know it's a line, that's all we need, right? Like 2 points is all we need to make a line. We went from here to here. So we know our direction is this way. Don't just start here, though. This line definitely goes from a negative infinity to infinity. So we would definitely get all of these. Here's one place you now want to be very, very careful. We don't want to put an arrow right here because now the arrows start to mean things. It means our direction. And if we start putting an arrow here, it means we're tending off in this direction, all right, on that right-hand side. So what you're instead going to do when that happens, you are going to put an arrow there, but we're going to put an arrow that feeds into the bottom of this, and that just is indicating that we are coming from this direction infinitely, but we're traveling in this direction. All right. When we get to a quiz, if you throw that other arrow on there, that'll be a problem if you say we're going down. Okay. The xy equation, again, just a substitution here. I'm going to take this one. So y equals 1 plus t, and I'm just going to replace the t. with what is it equivalent to over here. So if I solve that other equation for t, we would get what? T is equal to 1 minus x. Think about what that now simplifies to be. That's 2 minus x. Don't we have an equation whose y-intercept is 2, like this is telling us we should have? And our slope is a negative 1. Down 1, right 1, down 1, right 1. So then it all works together, and pretty good indication that we are correct. Okay. All right. That should have been done yesterday. So I do want to get at least these first couple of problems started so we can get this done tomorrow. So go to the next set of notes. What we just did is just an introduction to parametric curves, what they are, how we can find points, how they relate to each other. What this section now does is it gets into all the stuff that we've done throughout the year, maximums, minimums, velocities, slopes, all that stuff, but with these types of functions. All right, so that's why it's called the calculus of parametric curves. At the top, we've already talked about x position. Y position is defined as two separate functions. If I want the derivative, we've actually kind of already have done this. So think about x equals f of t. So if I give you some function, x equals f of t, and I ask you for the derivative of this, we would write that as dx dt would equal, and then whatever we would have over here. If I gave you y written as a function of t, we would get dy dt to equal, and whatever the derivative of that function is. Well, if I want dy dx, so change in y over change in x, because we're still just looking for slope, our whole delta y over delta x. To create that, what we would need to do is to take the dy dt fraction that we would get from this derivative, divide it by the dx dt fraction, because when we do that, wouldn't the dt's cancel? And what we would then be left with is change in y over the change in x. So that's how we can find the slope in terms of x and y with a parametric equation. So if you go down to number 1, if I wanted you to find dy dx, what we would now know is that if I took the derivative of this equation, that gives me dx dt. That's the change in my x position according to time, and that would be 2t. So that's not our answer. If I took the derivative of this one, that's my vertical change with respect to time, and that's 4t cubed. If, again, this is the ratio that I want, so if I want dy over dx, to create that, I need to take the dy dt, divide it by the dx dt, so the dt's will cancel. So for this particular problem, think about what those are. Dy dt was the 4t cubed, so that's going to be our numerator. The dx dt here is a 2t. That's going to be your denominator. Simplify that to give us 2t squared. That is kind of our answer. Try that again. So this is everything that we were supposed to do, we've done. However, if at all possible, we want our change to be in terms of x. So we would like this to not be t's if at all possible. And in this case, it is possible, because if you look right here, doesn't t squared equal x? So I can actually do a real quick substitution and get rid of t squared, because what t squared was equal to is an x. So the slope in this case, change in y with respect to x, is always twice my x coordinate. Okay. All right, number 2, same process. So if I want the derivative of this first one, hopefully we got this. I'm going to erase this right now. A little room to operate. The derivative of the first one would be dx dt, and then that's just secant t tangent of t. The derivative of the y would be dy dt, my vertical change over my time. And the derivative of tangent is secant squared of t. If I want dy dx, which is what we do want, the slope on an xy plane, then we've got to do the dy dt, which we have in this problem to be secant squared of t, divided by the dx dt, which for this one is secant tangents. We're going to evaluate it at pi over 4. So you can plug it in right now if you want. If you don't want to simplify, it doesn't necessarily matter. I'm guessing most of us probably would see this and decide to reduce those secants down a little bit. So let's do that. Secant squared divided by secant would just give you a secant. And then we want to evaluate this at pi over 4. So now we actually want to know what is the slope at a particular time. Tangent of pi over 4 is the easy one. It's just a 1. To do the secant is the reciprocal of cosine of pi over 4. So let's write this as 1 over the cosine of pi over 4. And that would just be 1 over root 2 over 2. The reciprocal of that is then 2 over root 2. Free response-wise, that's acceptable. They won't be mad if you don't rationalize your denominator. But if we do rationalize it, then you should just get root 2. All right. So that's our slope now at that particular time. All right, what do we got here? Yeah, we'll do 3. We should get 3 done, and then that'll make sure that we get done tomorrow. So the next thing that we've been doing all year is writing the equation of a line tangent to a curve. So we can certainly do this with these as well. So same process where in order to do that, we need a point where our line is tangent to the curve at, and then we want to know what is our slope at that particular point. Same thing we would have done for every one of these problems all year. To figure out our x coordinate, so now understand what each of these means, this gives us our x position at any time that we want it. The time we want is pi over 4. So what I want is, what is my x position at pi over 4? And that would just be 2 times the cosine of pi over 4, whatever that is. So the x position at this time should be 2 times the cosine of pi over 4, which is root 2 over 2. These will cancel, and our x position at that time is just a root 2. So now we can go back to our point. We now know that the x coordinate is root 2 over 2. Same process with the y. Take your y now. We want our y position at this time. So that'll be 2 times the sine of pi over 4. The sine of pi over 4 is also a root 2 over 2. So my y value is also root 2 for our y coordinate. And then we have our point. All right, root 2 over 2. Wait, hold on a minute. My bad. It should just be root 2's, right? So root 2 for x, and then root 2 for your y. Our slope now is what we just got done doing. So it's the same thing that you would have done in problems number 1 and 2. If I now want the slope, my change in y over my change in x, that is going to be the dy dt divided by the dx dt. So dy dt, the derivative of the y equation, should become 2 cosine of t. The derivative of the x equation would be 2, and then the derivative of cosine is a negative sign. So we'll go negative 2 sine of t. And then we just want to evaluate this at the time you are given to work with, which is pi over 4. So 2's will cancel. The cosine of pi over 4, the sine of pi over 4 are both root 2 over 2's. So root 2 over 2 divided by negative root 2 over 2. You probably don't even necessarily need to write that to know that our slope is going to be a negative 1. Once we have the 2 pieces of information that we needed, then you're all set to write your equation. So we would now say y minus root 2 equals the slope times x minus root 2, and then that is our tangent line to the curve at that particular time. All right. All right, let me see here. jump down to 6 just because it's the quickest and easiest one. And then we won't do 4 and 5 at all. It's a little overkill anyway with these. These are pretty simple. So go down to number 6. If I want you to write the equation of your line, we need x and y, and we need our slope. So these should be really quick. Take your x, or your time of -1, plug it in for your times. Our x position at that time should be what, 5? So that's going to be our x. If you throw that into your y, so y of -1 is a -1 to the 4th. So that's a +1. And then that's our point. Our slope then, dy dx, is going to be the dy dt, which would be 4t cubed as your numerator. And then in your denominator, the derivative is what, 4t. We can simplify that, I suppose. That's just t squared. And then if we evaluate that at the time of a -1, we get a +1. So then that's our slope. We have that. We can now write our equation. And we're on our way. All right. So hopefully easy enough. Just being able to find your derivative and then using that to find the equation of our line tangent. Okay. We're going to call it a day. We got a couple minutes left. It's a little too much anyway. I don't know. As I looked at these this morning, I don't know why I give you 4 of these because it's pretty easy. So bring this tomorrow, and then this should allow us to get that back page done. And again, no quiz tomorrow, so don't worry about that. But have this tomorrow, and we're going to finish this for the class period tomorrow. Okay? All right, so take a couple minutes, enjoy. All right, have a good night. All right, we'll see you guys all tomorrow. Okay? You too.